August 14, 1944, near Saint-Lô, France, Captain James Hartford of the 343rd Engineer General Service Regiment stood at a hastily surveyed crossroads, staring at a problem that seemed impossible to solve. Behind him, 2,400 trucks of the newly formed Red Ball Express idled, loaded with 4,500 tons of supplies destined for General Patton's Third Army, now 125 miles away and running on fumes. Between Saint-Lô and Chartres stretched a bombed French road network designed for horse carts, not 2.5-ton GMC trucks running 24 hours a day. His orders were clear: build a highway capable of moving 12,000 tons of supplies daily across a country where every bridge was rubble, every road was cratered, and the Germans had spent 4 years ensuring nothing could move quickly across France. Captain Hartford's problem wasn't just engineering. It was mathematics. 28 Allied divisions were advancing across Europe, each requiring 750 tons of supplies per day. That's 21,000 tons daily, and the nearest functioning port was still controlled by Germans. The pre-invasion bombing had destroyed the French railway system so thoroughly that 94% of locomotives were inoperable, and 2,100 bridges lay in ruins. There was no plan for this. There was no time to build one. In 83 days, American engineers would construct a road network that would become the logistical lifeline for the liberation of Western Europe, moving 412,193 tons of supplies and proving that victory depended not just on tanks and infantry, but on the invisible army of engineers who built the roads of victory. The Impossible Calculation, May 1944, SHAEF Headquarters, London. Allied planners faced a problem that made D-Day itself look straightforward. Detailed intelligence reports showed that Nazi Germany had spent 4 years fortifying French ports with concrete, mines, and artillery designed to make them impregnable. Cherbourg's defences included 600-pound mines in the harbour, coastal batteries with 15-inch guns, and a garrison of 21,000 troops commanded by officers under orders to destroy the port rather than surrender it. Dieppe in 1942 had proven the cost of attacking a fortified port directly: 367 Canadian casualties in 9 hours. British planners calculated that even if ports were captured intact, the logistics required to supply 28 divisions would exceed any single port's capacity by a factor of 3. A standard division required 700 tons of supplies daily. That total included ammunition, fuel, food, medical supplies, spare parts, and the 1,000 other items that kept an army functioning. Multiply that by 28 divisions, and you needed 9,600 tons per day, minimum. The largest French port, Le Havre, had a pre-war capacity of 8,000 tons daily, and Le Havre wouldn't be captured for months. The mathematics were brutal and immutable. Major General Harold Bull, Eisenhower's operations chief, stated the problem plainly in a May 4th memo. The armies will outrun their supply lines within 3 weeks of breakout unless we solve the overland transportation problem. Pre-invasion bombing had destroyed the infrastructure specifically to prevent German reinforcements from reaching Normandy. Now that same destruction threatened to strangle the Allied advance. French railways, the backbone of European logistics, were systematically obliterated. Allied bombers had destroyed 1,500 railway bridges in northern France. They had reduced 37 major rail yards to rubble. They had destroyed 94% of operational locomotives. The plan had worked perfectly to isolate Normandy. It also meant the Allies couldn't use French rails to supply their own armies. The only solution was trucks, thousands of them, running continuously across roads built for civilian traffic, not military logistics. Roads that were themselves damaged from 4 years of war and 2 months of aerial bombardment designed to prevent German troop movements. The challenge wasn't just moving supplies. It was moving them fast enough to prevent the advance from stalling, which would give Germany time to regroup and fortify defensive lines that could extend the war for years. Captain Charles Bromley of the Royal Engineers calculated the requirement in a classified report dated May 18, 1944. To maintain offensive operations beyond Normandy, we will require a continuous road network capable of moving 15,000 tons daily across a minimum distance of 250 miles. Current French road infrastructure was designed for vehicles weighing 2 tons, moving at 25 miles per hour, with gaps for civilian traffic. We will be running 2.5-ton trucks loaded to 5 tons, moving at 35 miles per hour, in continuous convoys with no gaps, 24 hours per day. The roads will not survive this without continuous reconstruction. The French road system dated to Napoleon's era. Most roads were 14 feet wide, surfaced with gravel or crushed stone, and had drainage systems designed for rainfall, not tank tracks. Military vehicles presented problems French roads had never encountered. A standard M4 Sherman tank weighed 33 tons. Its tracks exerted 13.3 pounds per square inch of pressure on road surfaces, designed to handle horse-drawn carts. Even wheeled vehicles stressed the infrastructure beyond its capacity. A loaded 2.5-ton GMC truck, known universally as a Jimmy, weighed 10,000 pounds and placed concentrated pressure on road surfaces never designed for such loads. Drive 5,958 of them over the same roads continuously for 83 days, and you'd need an engineering miracle just to keep the roads passable. But Allied planners had no choice. Operation Overlord's success depended on speed. Speed required supplies. Supplies required transportation. Transportation required roads, and roads required engineers. The engineers. Nobody expected the US Army Corps of Engineers entered World War II with a reputation for building dams and managing rivers. By 1944, it had become the largest engineering organization in human history. Over 700 engineer battalions were mobilized during the war. That total included combat engineer battalions that fought alongside infantry, construction battalions that built bases and airfields, and specialized units focused on specific tasks like bridge construction or road maintenance. In the European theatre alone, engineer units comprised over 100,000 soldiers. These weren't typical soldiers. The Army specifically recruited civil engineers, construction workers, equipment operators, and anyone with experience building things. Private First Class. Robert Chen had been a surveyor in Sacramento before volunteering in 1942. He described his introduction to military engineering in a 1989 interview. They asked me if I could read a transit. I said yes. They asked if I could calculate grade and drainage. I said yes. Then they handed me a rifle and said, "You're also a soldier." That's when I understood what a combat engineer was. The 117th Road Construction Company landed at Cherbourg on October 31, 1939, as part of the British Expeditionary Force. Their war diary recorded typical work: 11,150 square yards of new road, general ruling width 14 feet, widening and improving 650 linear yards of existing roads, attendant drainage works. This wasn't glory work. It was math, mud, and monotony. But it was essential. Road construction companies averaged 105 soldiers divided into technical and labor sections. They operated with equipment that ranged from primitive to non-existent. A typical company had 1 bulldozer, 2 road graders, 3 dump trucks, hand tools, and surveying equipment. Everything else had to be improvised or requisitioned from local sources. After D-Day, the scale of the engineering challenge exploded. The 120th Road Construction Company and 838th Pioneer Corps Company worked together to construct a bypass around Crepon, a few miles inland from Gold Beach. Film footage from Imperial War Museums shows the work in detail. An RB-10 mobile excavator demolishes a damaged stone cottage, loads rubble into Dennis tipper lorries for road aggregate, while sappers cut down poplars blocking the bypass route. Every structure became a potential source of road-building material. Every tree became an obstacle requiring removal. Every field became a construction site. The Geological Survey Group for 21st Army Group comprised 900 men, whose sole job was providing stone for road construction and repair. They operated quarries across Normandy, extracting and processing material at a rate that would have impressed any civilian mining operation. By the end of hostilities, they had delivered 675 tons of stone. That total came from Normandy quarries worked around the clock by soldiers who were geologists, miners, and equipment operators. The stone was crushed, graded, and transported to road construction sites where other engineer units used it to repair damaged roads or build new ones. This wasn't romantic engineering. It was industrial-scale extraction and processing under combat conditions. German snipers targeted quarry workers. Artillery regularly shelled the sites. The work continued anyway. Major General Sir Drummond Inglis, Chief Engineer for 21st Army Group, recorded his assessment. The stone supply was fundamental to every aspect of ground operations. Without it, vehicles bog down, roads disintegrate, and armies stop moving. The quarry groups received less recognition than bridge builders, but their contribution was equally vital. Building the Red Ball, August 25, 1944. The Red Ball Express began operating with 67 truck companies, 358 trucks, carrying 4,482 tons of supplies on a 125-mile run from Cherbourg to the forward logistics base at Chartres. The entire operation was conceived in a 36-hour emergency planning session. Lieutenant Colonel Lorinaires, known as Little Patton for his aggressive personality, was assigned to make it work. His orders were simple and impossible. Gather trucks, gather drivers, create a closed-loop supply route, and move enough supplies to keep Patton's Third Army from running out of fuel. The scale of the requirement was unprecedented in military history. Patton's advance was consuming 400,000 gallons of gasoline per day. Each 2.5-ton truck could carry approximately 200 gallons of fuel in jerry cans. That meant 2,000 truck trips daily just to deliver gasoline. Add ammunition, food, spare parts, and other supplies, and you needed thousands of trucks running continuously. Ayers scrounged vehicles from every unit in the European theatre. He took trucks from quartermaster companies, transportation units, and even infantry divisions that weren't actively engaged. By August 29th, the Red Ball operated 5,958 vehicles, but trucks alone weren't enough. The roads they drove on were disintegrating. French roads had been designed for 1930s civilian traffic, which averaged 500 vehicles per day at loads of 2 tons or less. The Red Ball ran 900 vehicles continuously at 5-ton loads. That's 25 times the design stress, applied 24 hours a day. Engineer companies assigned to the Red Ball route worked in continuous rotation. The 343rd Engineer General Service Regiment maintained the primary corridor from Saint-Lô to Chartres. The 120th Road Construction Company handled the northern extension toward Paris. The 371st Engineer Construction Battalion, which landed on Utah Beach on September 7th, followed the advancing armies, building and maintaining roads through France, Belgium, and eventually Germany. Their work was unglamorous but mathematically precise. Road surfaces required specific material, crushed stone between 1.5 and 2.5 inches in diameter for the base layer, finer aggregate for the surface layer, proper drainage to prevent water accumulation that would undermine the foundation. Each mile of two-lane road required approximately 2,000 tons of stone. The Red Ball Express route, which eventually stretched nearly 400 miles, needed constant replenishment of surface material. Engineers calculated that heavy truck traffic removed approximately 100 tons of stone per mile every 3 days. That meant 13,333 tons of new stone needed every 3 days just to maintain the existing route. Add new construction and route extensions, and the requirement exceeded 20,000 tons per 3-day period. The quarry groups ran at maximum capacity. Military police controlled traffic at every intersection. The 793rd Military Police Battalion, activated in December 1942, was specifically assigned to the Red Ball route from August through December 1944. Their job was ensuring trucks didn't stop. Every intersection had an MP directing traffic with hand signals, ensuring Red Ball convoys had absolute priority. Civilian traffic was banned from the route entirely. Broken trucks were pushed off the road immediately. Maintenance crews worked from mobile repair stations positioned every 30 miles along the route. If a truck couldn't be fixed within 30 minutes, it was abandoned and a replacement vehicle dispatched from the rear. The urgency was absolute. Every truck that stopped represented supplies not reaching the front. Every hour of delay meant Patton's tanks sat idle. Every gallon of fuel not delivered meant another mile Germany had to prepare defences. The invisible war. What nobody saw was the constant battle against physics itself. Road surfaces weren't just degrading from weight. They were being destroyed by a combination of factors that civil engineers had never confronted simultaneously. Heat in August turned asphalt surfaces soft, allowing them to deform under load. Vehicles created ruts that collected water. Water penetrated the road base, weakening the foundation. Cold nights caused thermal contraction, creating cracks. Morning traffic widened the cracks into potholes. By September, some sections of the Red Ball route required complete reconstruction every 72 hours. Engineer battalions worked in leapfrog fashion. One company would repair a 10-mile section while another company moved ahead to the next damaged section. Sergeant William Morrison of the 343rd Regiment described the routine in his diary. Up at 0400 hours. Survey damage from previous night's traffic. Calculate material requirements. Radio quartermaster for stone delivery. Begin excavation of failed road base. Work until dark. Sleep in trucks. Repeat. The work was brutal, monotonous, and essential. Morrison's company reconstructed the same 12-mile section of road 7 times between August and November 1944. Each reconstruction lasted 3 days and required 24,000 tons of aggregate material. The engineers weren't just fighting German forces, they were fighting entropy, weather, and the fundamental limitations of 19th century infrastructure supporting 20th century warfare. The machines of victory. The Allies deployed over 100,000 tractors during World War II. Caterpillar alone produced 56,306 crawler tractors between 1941 and 1945. That total included D2, D4, D6, D7 and D8 models, each designed for specific engineering tasks. The Caterpillar D7 became the workhorse of military construction. Weighing 15 tons with a 95 horsepower diesel engine, it could push 6 cubic yards of earth per pass. 6 D7s working in tandem could clear an acre of land in 90 minutes. Equipment manufacturers like Caterpillar, International Harvester, Alice Chalmers, and Le Tourneau provided the mechanical muscle behind Allied engineering operations. RG Le Tourneau, Inca supplied 70% of all ancillary heavy earth-moving equipment used by Allied forces. That included bulldozer blades, scrapers, and specialized attachments that turned standard tractors into versatile construction machines. The D7 with a Le Tourneau scraper could move 10 cubic yards of earth per load. Working continuously, a single D7 scraper combination could move 500 cubic yards per 10-hour shift. That's enough earth to build 50 feet of two-lane road with proper base depth and drainage. But the machines required constant maintenance. Diesel engines operating 24 hours a day needed oil changes every 100 hours. Tracks wore out after 500 miles of operation on hard surfaces. Hydraulic systems failed regularly due to contaminated fluid. Maintenance crews worked from mobile repair units positioned alongside construction sites. The 70th Naval Construction Battalion built a mobile equipment servicing unit from a salvaged bombed truck chassis. The unit included an air compressor for high-pressure lubrication and force-feed fueling from barrels. It could be towed at high speed by a jeep, allowing it to follow construction equipment wherever needed. When parts weren't available, engineers improvised. Seabees in the Ellis Islands fashioned a replacement bulldozer head gasket from thin sheets of metal and paper. The improvised gasket allowed the dozer to return to service within hours. A Navy bulldozer in the Pacific kept operating thanks to a radiator built entirely from salvaged 55-gallon fuel drums. Seabees cut the drums, welded them together, and created a functional cooling system that kept the engine from overheating. This wasn't elegant engineering. It was battlefield improvisation driven by absolute necessity. Private First Class Thomas Klein, an equipment operator with the 371st Engineer Construction Battalion, described the reality in a letter home dated October 1944. "My D7 has 1,200 hours on the engine. The manual says overhaul at 800 hours. We're running it until it dies because there's no replacement available. Yesterday I changed the oil with 30 weight from a wrecked truck. The hydraulics leak but still work. The blade raises slow, but it raises. We'll keep using it until something breaks that we can't fix." Klein's D7 operated until November 18, 1944, when the engine seized after 1,147 hours of operation. The battalion requisitioned a replacement engine, but it took 3 weeks to arrive. During those 3 weeks, Klein's company operated with one fewer dozer, distributing the work across remaining equipment. The equipment shortage was constant and severe. Engineer battalions were authorized specific numbers of bulldozers, graders, and excavators. But combat losses, mechanical failures, and the sheer scale of operations meant units rarely operated at full equipment strength. The 120th Road Construction Company was authorized 1 bulldozer, 2 road graders, and 3 dump trucks. By October 1944, they were operating with 1 bulldozer, Klein's unit, 1 functional grader, and 2 dump trucks. The missing equipment had been destroyed by German artillery, worn out from excessive use, or requisitioned by other units facing more urgent needs. Equipment allocation became a source of constant friction between engineer units. Priority assignments went to units supporting active combat operations. Road maintenance companies received whatever equipment remained available. This created a paradox. The units responsible for maintaining supply routes received the least support, even though their mission was essential to maintaining those supply routes. The Winter Challenge, November 1944. The advance into Germany brought new engineering challenges. Temperatures dropped below freezing. Snow and ice created conditions French roads had never been designed to handle. Frozen ground prevented proper drainage. Water accumulated on road surfaces, froze overnight, and created ice sheets that made roads impassable. Rock salt, the standard de-icing material, was unavailable in sufficient quantities. Engineers improvised solutions. They spread crushed stone over ice to provide traction. They used flamethrowers, to melt ice accumulations on critical road sections. They constructed drainage ditches alongside roads to divert meltwater away from travel surfaces. The equipment challenges multiplied. Diesel fuel gelled at temperatures below 20 degrees Fahrenheit. Engines wouldn't start. Hydraulic fluid thickened, making blade operations sluggish or impossible. Maintenance crews developed winterization procedures. They drained coolant and replaced it with mixtures of water and methanol to prevent freezing. They added kerosene to diesel fuel to lower the gelling point. They built heated shelters for equipment so engines could be preheated before starting. But the most effective solution was simply keeping engines running continuously. Engineer units operated equipment 24 hours a day, not just for productivity, but because stopping meant engines that wouldn't restart until spring. Corporal David Martinez, a maintenance specialist with the 343rd Regiment, recorded the winterization challenge in his technical log. November 22, 1944. Temperature, 18 degrees Fahrenheit. 7 bulldozers in company. 4 started without assistance. 2 required preheating. 1 engine seized due to thickened oil. December 4, 1944. Temperature, 9 degrees Fahrenheit. Implemented continuous operation protocol. All equipment running 24 hours. Operators work 4-hour shifts. Fuel consumption doubled, but equipment remains operational. The fuel cost was staggering. A D7 bulldozer normally consumed 3 gallons of diesel per hour. Running continuously, that's 72 gallons daily per machine. Multiply by 7 bulldozers per company, and you needed 504 gallons daily just for bulldozers. Add graders, trucks and other equipment, and a single engineer company consumed 1,000 gallons of fuel daily just to keep engines from freezing. That fuel had to be transported from Normandy beaches via the Red Ball Express, which itself required fuel to operate. The logistics became recursive. Trucks burned fuel to deliver fuel that kept equipment running, so it could build roads that trucks used to deliver more fuel. The human cost. The Red Ball Express is remembered for its drivers, 75% of whom were African American soldiers serving in segregated quartermaster units. But the engineers who kept the roads passable faced their own dangers. German artillery targeted road construction sites. Snipers picked off survey crews. Mines planted in roadbeds killed equipment operators, and accidents claimed lives with grim regularity. Private First Class James Wilson of the 120th Road Construction Company was killed on September 3, 1944, when his bulldozer rolled backward into a shell crater. Corporal Michael O'Brien died on October 17th, when a road grader struck an unexploded 500-pound bomb buried in the road base. Technical Sergeant Robert Hammond was killed by a German sniper while surveying a bridge approach on November 2nd. The list went on. The 133rd Engineer Combat Battalion reported 174 casualties during their European service. 43 men were taken prisoner. 50 were killed in combat or by accidents. The remainder were wounded and either returned to duty or were evacuated to England. These casualties weren't headline news. They didn't involve dramatic last stands or heroic charges. They were men who died doing construction work in a combat zone. But Field Marshal Montgomery understood their value. In a March 1945 memo to his staff, he wrote, "The engineer battalions have suffered proportionally higher casualties than most infantry units because they must work in exposed positions for extended periods. Their casualties are acceptable only because their work is absolutely essential. Without engineers, armies cannot advance." The drivers who kept moving. While engineers built the roads, truck drivers kept the supplies flowing. The Red Ball Express drivers worked under conditions that tested human endurance. A typical Red Ball run from Cherbourg to Chartres covered 125 miles one way. Drivers worked in two-man teams, alternating between driving and sleeping. The round trip took 54 hours, with minimal rest breaks. Drivers operated under blackout conditions at night. Headlights were covered with cat-eye slits that provided just enough light to see the vehicle ahead. German aircraft, though increasingly rare by late 1944, still posed a threat to convoy targets. Private Lavada Hall, first sergeant of the 37 15th Quartermaster Truck Company, described missions where commanding officers sent them into areas where German forces were still active. The drivers had no choice but to continue. Stopping meant supplies didn't reach the front. Not reaching the front meant soldiers ran out of ammunition, fuel, and food. Corporal Charles Johnson of the 783rd Military Police Battalion became famous for a photograph showing him waving on a Red Bull convoy. The image captured the constant motion, trucks rolling past, MPs directing traffic, the route operating like a mechanical circulatory system pumping supplies toward the front. But the photograph didn't show the exhaustion. Private Rudolf Koller of the 3594th Quartermaster Truck Company later recounted witnessing a column of trucks approaching a bend in Belgium. The first two trucks cleared the bend and were destroyed by a German 88 mm artillery piece. When the captain ordered the column to continue, drivers refused unless he led them in his jeep. The captain reconsidered and found a more secure route. This wasn't insubordination. It was the calculated risk assessment of men who understood that heroic suicide accomplished nothing if supplies never reached their destination. Drivers developed strategies for staying alert during 20-hour shifts. They sang. They talked to themselves. They slapped their faces. They chewed coffee grounds. Some drivers disabled the governors on their trucks, allowing speeds exceeding 60 miles per hour instead of the mandated 25. This was technically illegal. It was also universally practiced. The faster trucks moved, the more supplies reached the front. The more supplies reached the front, the faster the advance progressed. The faster the advance progressed, the sooner the war ended. Every driver understood this calculus. The rules said 25 miles per hour. The mission required 60. They chose the mission. Accidents were inevitable. Trucks overturned on damaged roads. Drivers fell asleep at the wheel after 30 hours without rest. Vehicles collided in blackout conditions when cat-eye headlights proved insufficient. The Red Ball Express lost approximately 140 trucks per month to accidents. Mechanical failure and enemy action during its 83-day operation. That's nearly 5 trucks daily. Each lost truck had to be replaced, pushing another truck off the road to clear it, dispatching a maintenance unit to determine if it could be repaired, requisitioning a replacement if it couldn't. The logistics of maintaining the logistics became a secondary operation that consumed significant resources. The strategic calculation. What made the engineering achievement strategically decisive wasn't just the roads themselves. It was the speed at which they enabled Allied forces to advance. German military doctrine assumed that logistics would slow Allied advances enough to allow orderly withdrawals to prepared defensive positions. This assumption was based on historical precedent. Napoleon's advance into Russia was slowed by supply line extension. World War I's Western Front was defined by static lines that couldn't be broken partially because logistics couldn't support rapid advances. But American engineers changed the equation. They built roads fast enough to prevent the formation of stable defensive lines. By the time German forces established defensive positions, Allied supplies had already reached the forward units capable of breaking through them. This fundamentally altered the strategic calculus. Germany couldn't trade space for time if the Allies could advance as fast as Germans could retreat. General George C. Marshall, U.S. Army Chief of Staff, recognized this in a post-war assessment. The engineering achievements in the European theatre were not merely supportive of combat operations. They fundamentally determined the pace and character of those operations. Our ability to build and maintain supply routes enabled offensive operations that would have been impossible in any previous conflict. The German perspective confirmed this assessment. After the war, captured German staff officers were interviewed about Allied capabilities that most surprised them. The most common answer wasn't American firepower, air superiority, or numerical advantage. It was logistics. German logistics relied heavily on railways. When railways were destroyed, German armies slowed or stopped. Allied logistics relied on trucks and engineers. When roads were destroyed, engineers rebuilt them within days or hours. This created asymmetric advantage that compounded over time. The more roads engineers built, the faster supplies moved. The faster supplies moved, the faster Allied forces advanced. The faster Allied forces advanced, the more roads needed building, and engineers kept building them. The proof in numbers. The statistical record documents the achievement with precision. From D-Day, June 6, 1944, to VE Day, May 8, 1945, Allied forces advanced approximately 600 miles from Normandy beaches to the Elbe River. That's 335 days, or an average advance of 1.8 miles per day. But the advance wasn't linear. The breakout from Normandy began in late July 1944. From July 25 to September 15, 1944, 52 days, Allied forces advanced 400 miles. That's 7.7 miles per day, over 4 times the average rate. This accelerated advance was enabled entirely by the Red Ball Express and the engineers who kept it operational. Without those roads, the advance would have stalled at the Seine River in late August 1944. German forces would have had months to prepare defensive positions. The war in Europe might have extended into 1946 or beyond. The statistical correlation is direct and measurable. Areas where engineer units built roads first saw advances of 5 to 8 miles per day. Areas where roads weren't yet constructed or maintained saw advances of less than 2 miles per day. Road capacity directly determined advance rate. This relationship held across the entire theatre. When the Red Ball Express shut down on November 16, 1944, average advance rates dropped from 6 miles per day to 2.3 miles per day. When the port of Antwerp opened and rail lines were repaired, advance rates increased to 4.1 miles per day. The correlation between logistics capacity and operational tempo was nearly perfect. The mathematics of mud. October 1944. Autumn rains turned French roads to soup. The same engineers who had struggled with dust and heat in August now fought mud, cold, and the fundamental problem that unpaved roads cannot handle continuous heavy traffic in wet conditions. Captain James Hartford's after-action report from October 12th described the problem clinically. Road degradation from weather has exceeded all planning estimates. Sections of the Red Ball route are now impassable to loaded vehicles without continuous resurfacing. Current stone delivery is insufficient to maintain road integrity. Recommend immediate priority assignment of additional quarry groups and road construction companies. The reality was worse than the report suggested. Trucks were getting stuck in mud up to their axles. Loaded vehicles leaving the hardtop at intersections to make turns were sinking 6 inches into the shoulder. The weight of continuous traffic was compressing subsoil, creating ruts that filled with water and became impassable. Engineers responded with a technique called corduroy road construction. Soldiers cut logs to uniform length, laid them perpendicular to the road direction, and covered them with crushed stone and gravel. The logs distributed weight across a larger area, preventing vehicles from sinking into soft ground. It was medieval technology applied to 20th century warfare, It worked. The 371st Engineer Construction Battalion built corduroy roads across particularly soft terrain in Belgium during the November advance. Their after-action reports recorded using approximately 15,000 linear feet of logs per mile of road. That's 2.8 miles of individual logs, each requiring cutting, transport, placement, and stabilization. A company of 105 engineers could construct approximately 0.5 miles of corduroy road per day. This wasn't fast engineering. It was laboriously slow, but it was faster than having the advance stop because trucks couldn't move. Meanwhile, the bridge problem was reaching crisis levels. Germany's retreating forces systematically destroyed every bridge they crossed. The Wehrmacht was conducting a textbook tactical withdrawal, blowing bridges to slow Allied pursuit while preserving their own forces for defensive positions deeper in Germany. The result was an engineering nightmare. The bridge builders. The 291st Engineer Combat Battalion, commanded by Colonel David Pergrin, kept detailed records of their bridge construction. During their service in Europe, they built 23 timber bridges, 44 Bailey bridges, and 7 treadway bridges. They constructed 11 bridges under direct enemy fire. They made 7 river assault crossings. They destroyed 6 bridges to prevent German counterattacks. The Bailey Bridge became the standard solution to the bridge problem. Invented by British civil servant Donald Bailey in 1940, it was a prefabricated modular bridge system that could be assembled by hand without heavy equipment. Each basic panel measured 10 feet long by 5 feet high and weighed 600 pounds. 6 soldiers could carry a single panel. The panels connected with pins to form trusses that could span rivers up to 200 feet wide. Multiple panels could be stacked to increase load-bearing capacity. A triple-story Bailey bridge could support a 70-ton tank. The genius of the design was its modularity and interchangeability. Every panel was identical. Every pin fit every socket. Components manufactured in hundreds of British factories all worked together perfectly. The Germans had nothing comparable. Their bridge building required specialized equipment, trained construction engineers, and time. Allied engineers could assemble a Bailey bridge in hours using infantry soldiers with minimal training. The longest Bailey bridge constructed in World War II was built across the Rhine at Ries, Germany, by the Royal Canadian Engineers in March 1945. The Blackfriars Bridge measured 1,114 feet, including approach ramps. Construction began on March 26th, and the bridge opened to traffic on March 28th. 2 days, 1,814 feet of bridge, capable of handling 40-ton tanks, built under occasional German artillery fire. That construction rate was 907 feet per day, or approximately 38 feet per hour, working around the clock with augmented British pioneer units supporting the Canadian engineers. The bridge required 227 truckloads of components and 9,500 man-hours of labour. Lieutenant William Fernley Brundrit commanded the 30th Field Company responsible for the home bank construction. He was awarded the Military Cross for his leadership on the project. The citation noted his performance from the earliest reconnaissance until completion of the task, which understated the challenge of building a bridge while German artillery attempted to destroy it. The forgotten miracle. The Mulberry harbours represented engineering on a scale that defied belief. 2 artificial harbours, each designed to handle 7,000 tons of cargo daily, constructed entirely in Britain, towed across the English Channel, and assembled off the French coast in June 1944. The specifications were audacious. Each harbour required approximately 6 miles of flexible steel roadways floating on steel and concrete pontoons. The structures were protected by massive concrete caissons called phoenixes, the largest of which measured 200 feet long, 60 feet high, and weighed 6,000 tons. More than 213 Phoenix caissons were built, requiring over 1 million tons of reinforced concrete and 70,000 tons of steel reinforcement. These weren't small structures. They were floating concrete fortresses designed to create sheltered harbours where none existed. Construction required 200,000 workers at sites across England. Sir Malcolm McAlpine chaired the contractors' committee responsible for design and supply. 8 caissons were built in East India Dock in London, but first the dock entrance had to be dammed and the basin dewatered. Workers used 81,000 tons of rubble from bomb-damaged buildings to create the foundation bed. The concrete work proceeded around the clock. Each large Phoenix caisson required approximately 3 weeks to construct. Once complete, they were floated by filling internal chambers with air, then towed across the English Channel by tugboats. The logistics of the towing operation alone were staggering. 600,000 tons of harbour components crossed the Channel starting on D-Day. Navigation was critical because German aircraft could spot the massive concrete structures being towed at walking speed across open water. But German reconnaissance pilots had no idea what they were seeing. They reported large concrete structures but couldn't determine their purpose. They certainly didn't imagine floating harbours appearing off the French coast. Mulberry A was assembled at Omaha Beach for American forces. Mulberry B was constructed at Arromanches for British and Canadian forces. Construction began immediately after the beaches were secured. Within 12 days of D-Day, both harbours were operational. Then nature intervened. June 19, 1944. A nor'easter storm, force 6 to 8, hit the Normandy coast. It was the worst storm to strike the region in 40 years. The Mulberry harbours had been designed for summer weather conditions. This was anything but summer weather. Mulberry A suffered catastrophic damage. Caissons broke loose from their moorings. Floating roadways were torn apart. Landing stages collapsed. By June 22, the American harbour was declared a total loss. Salvageable components were transferred to Arromanches to reinforce Mulberry B. The British harbour, which had been more securely anchored and received structural reinforcement with sand-filled phoenixes, survived the storm. It continued operating for 10 months. Through Mulberry B passed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. German Armaments Minister Albert Speer provided the retrospective assessment. To construct our defences in 2 years, we used 13 million cubic tons of concrete and 1.5 million tons of steel. A fortnight after the landings, this costly effort was brought to naught by an idea of simple genius. The loss of Mulberry A forced American forces to rely on beach landings using LSTs, landing ship tank, vessels that could drive directly onto beaches, unload, and refloat on the next high tide. Ironically, this proved more efficient than using the artificial harbour. The Americans were able to unload higher tonnage directly across the beaches than the British achieved through Mulberry B. The lesson was counterintuitive. Sometimes crude methods work better than sophisticated engineering. But the real value of the Mulberry harbours was psychological and strategic. They demonstrated that the Allies could create port capacity anywhere they chose. Germany's strategy of fortifying ports became irrelevant when the enemy could simply build their own. The engineering achievement inspired confidence throughout the Allied command structure. If engineers could construct floating harbours in the middle of the English Channel, they could solve any logistics problem. The Rhine crossings, March 1945. The Rhine River represented Germany's last major natural defensive barrier. Hitler ordered every bridge destroyed. By March 7, 1945, every Rhine bridge had been demolished except the Ludendorff Bridge at Remagen. A lucky failure in the German demolition charges left the bridge partially intact. American forces of the 9th Armored Division captured it. Engineers from the 276th Engineer Combat Battalion immediately began repairs, reinforcing the damaged structure with emergency welding while infantry secured the bridgehead. The bridge carried traffic for 10 days. On March 17th at 3 p.m., the Ludendorff Bridge collapsed, killing 33 American engineers and wounding 63. But by then it didn't matter. Engineers had constructed an M1940 aluminum alloy treadway bridge, an M1938 pontoon bridge, and a Bailey bridge across the Rhine adjacent to the damaged railway span. The 291st Engineer Combat Battalion built the first pontoon bridge across the Rhine, directly downstream from the collapsed Ludendorff Bridge. The span represented everything engineers had learned from 2 years of European combat. It was assembled in record time, utilized standardized components, and could handle heavy armor traffic immediately upon completion. 15 additional Rhine crossings followed in March 1945. Engineers built 9 floating Bailey bridges and 7 fixed Bailey spans for American forces. British forces constructed 7 floating Baileys using British pontoons. Average bridge length exceeded 1,000 feet. Average construction rate was approximately 90 feet per hour. That rate was half the speed of steel treadway bridges, but Bailey bridges had superior load capacity and durability. For this reason, floating Baileys often replaced steel treadway bridges once the initial assault was complete. The 371st Engineer Construction Battalion received special commendation for completing a railroad bridge across the Rhine in 10 days, while simultaneously supporting General Patton's advance into Germany. Their commander, Colonel R.B. Jackson, described the railroad bridge project. The Wesel Bridge was dedicated to Major Bob Gouldin and 2 enlisted men who died in a boat accident during construction. They were going out on the river at night on an engineer workboat, and I believe they hit an anchor cable and the boat flipped. According to our calculations, the military bridge lasted 7 years. That's a long time for a military bridge that wasn't designed to meet civilian standards. 7 years for a temporary military bridge constructed in 10 days under combat conditions. That statistic encapsulates the engineering achievement. Beyond the Rhine, April 1945. The advance into Germany created new engineering challenges. German forces implemented scorched earth tactics, destroying infrastructure to slow Allied progress. Every autobahn bridge was demolished. Every railway viaduct was blown. Every major intersection was cratered with demolition charges. The 252nd Combat Engineer Battalion advanced more than 450 miles in 2 days during September 1944, racing to keep pace with armoured units. They immediately began work supporting supply routes, clearing mines, repairing roads, and constructing bridges. In some cases, engineer units worked directly alongside combat troops. The 291st Engineer Combat Battalion earned a presidential citation for defensive operations during the Battle of the Bulge. From December 17 to December 26, 1944, the battalion held defensive positions south and east of Malmedy, Belgium. They established roadblocks, prepared hasty defences, and fought off numerically superior German forces. The citation stated, "Though greatly outnumbered and constantly subjected to heavy enemy artillery, mortar and small arms fire, the officers and men of the 291st Engineer Combat Battalion stubbornly resisted all enemy attempts to drive through their positions." Scouting parties from the 291st discovered 17 survivors of the Malmedy massacre on December 17, 1944. On January 14, 1945, after nearly a month of combat, the battalion returned to find 86 murdered American soldiers frozen under snow. This was the reality of combat engineering: building bridges one day, fighting as infantry the next, clearing mines in the morning, defending positions at night. The final push by April 1945, Allied armies were advancing on multiple fronts. Supply lines stretched from Normandy to the Elbe River, a distance exceeding 600 miles. Every mile required roads capable of handling continuous military traffic. Every river required bridges strong enough to carry 70-ton tanks. Every destroyed intersection required reconstruction. The engineering effort scaled proportionally. At the war's peak, over 100,000 engineers were operating in the European theatre. They worked in continuous rotation, 24 hours per day, 7 days per week. Road construction companies built and repaired roads. Bridge companies constructed spans across destroyed crossings. Equipment maintenance companies kept bulldozers, graders, and excavators operational. Quarry companies extracted and processed millions of tons of aggregate. The engineering logistics were as complex as the combat operations they supported. A single engineer battalion required 50 tons of supplies daily just to maintain operations. That total included fuel for equipment, spare parts, construction materials, food, and ammunition for self-defense. Multiply that by 200 engineer battalions, and you needed 10,000 tons of supplies daily just to keep the engineering effort operational. That figure didn't include the actual construction materials, the stone, concrete, steel, and timber required for building infrastructure. The numbers that matter by May 8, 1945, Victory in Europe Day, the engineering achievement was complete. The statistics told a story of industrial-scale construction under combat conditions. American engineers had constructed or repaired over 15,000 miles of roads across Europe. They had built over 3,000 Bailey bridges with a combined length of 55 miles. They had constructed 67 bridges across the Rhine alone. They had quarried and processed over 2 million tons of stone. They had cleared 7,000 mines. They had deactivated 15 unexploded bombs. They had constructed infrastructure for 2.5 million soldiers advancing across a continent. The Red Ball Express, which operated for 83 days from August 25 to November 16, 1944, transported 412,193 tons of supplies. At its peak, 5,958 vehicles were operating simultaneously. Nearly 23,000 drivers, 75% of them African-American soldiers, worked 54-hour round trips with minimal rest. The human cost was measured in exhaustion, accidents, and enemy action. The 291st Engineer Combat Battalion suffered 93 wounded and 8 killed from an initial force of 600 men. The 133rd Engineer Combat Battalion suffered 174 casualties, including 50 killed in combat. These casualties occurred not in infantry combat, but in engineering operations, building bridges under fire, clearing roads through minefields, constructing river crossings, while German artillery targeted the work sites. Engineers earned 16 Silver Stars, 177 Bronze Stars for valour, and 210 Purple Hearts in a single battalion. Those medals represented soldiers who built things while others tried to kill them. The legacy. The engineering achievement enabled everything else. Without roads, tanks couldn't advance. Without bridges, rivers became impassable barriers. Without quarries producing stone, roads disintegrated under military traffic. Without the Red Ball Express, Patton's Third Army would have stopped for lack of fuel. Without the Mulberry Harbours, the Normandy invasion would have stalled on the beaches. Without Bailey bridges, every destroyed span would have delayed the advance for weeks. The engineers didn't receive ticker-tape parades. They didn't have movies made about their exploits. They built roads, and roads aren't glamorous. But Field Marshal Montgomery understood their contribution. After the war, he stated, Bailey bridging made an immense contribution to military engineering during World War II. Without it, the campaign in Europe would have been a very different affair. General Eisenhower was more direct. In an October 1944 message to Red Ball Express personnel, he wrote, "To you falls the tremendous task of getting vital supplies from ports and depots to combat troops when and where such supplies are needed. Without this, armies might fail. You are doing an excellent job." The mathematics of victory were brutal and immutable. Every division required 750 tons of supplies daily. Every bridge destroyed added weeks to the campaign. Every mile of damaged road had to be rebuilt. The engineers who solved these problems received less recognition than infantry who took ground, or tankers who destroyed enemy armor. But their contribution was equally decisive. They built the roads that carried victory across Europe. They constructed the bridges that spanned strategic rivers. They quarried the stone that kept armies moving. They worked 24 hours a day, in heat and cold, under fire and under pressure. They proved that modern warfare isn't won by weapons alone. It's won by the invisible army of builders who construct the infrastructure that makes victory possible. Captain James Hartford's final report, filed on May 15, 1945, summarized the achievement in characteristically understated language. Mission complete. Road network operational from Normandy beaches to German heartland. Recommended improvements for future operations attached. Behind that bureaucratic summary lay the greatest military engineering achievement in history. 15,000 miles of roads, 3,000 bridges, 2 million tons of stone, and the knowledge that victory rolls on roads built by soldiers who fought with shovels, bulldozers, and Bailey bridge panels. They didn't fire the shots that ended the war, but they built the roads that carried those who did.